All right, so we're in section 11.7 now, and this section doesn't introduce anything new, but rather is kind of a summary of what we've done so far. So the focus here is on developing strategies for taking a series that you're given and testing it for convergence or divergence. So basically, we're going to go back over all of the tests that we talked about and discuss a little bit about when to use which test. And then we're going to do some examples where we apply this strategy. So when you're given a series, typically the first thing you want to do is look for divergence by using your test for divergence. The reason for that is because it's usually pretty quick to apply this test. Remember, the test for divergence looks at the sequence of terms of your series, and it checks to see if the limit of the sequence of terms is going to 0 or going to something else. If you apply the test for divergence, and if you see that the limit of your sequence of terms goes to anything other than 0, then you can stop right there and just say that the series diverges and move on. If the test for divergence does not show that the series diverges, in other words, if the limit goes to something other than 0, then it's still possible that the series diverges, but you don't know for sure. That test is inconclusive. So that's where you would move on to one of these other approaches. So following that, starting with number 2, we're looking at a variety of different series and series convergence tests, starting with 2 that apply to specific types of series. So the first is a p-series. If you recall, that's a series of the form where the terms are of the form 1 over n to some power p. We know that this series will converge if p is greater than 1 and will diverge if p is less than or equal to 1. Sometimes you have to manipulate this term here, this 1 over n to the p, to get it into that form. But if you can recognize your series as a p-series, this is a very quick and easy way to test it for convergence or divergence. Almost as easy as the geometric series. A geometric series, if you recall, are series that take this form, the sum of a r to the n minus 1 or a r to the n. Basically, each new term in the series comes from multiplying some common ratio r to the previous term. And we know from early on in this chapter that these series will converge as long as the absolute value of your common ratio is less than 1, but it will diverge if that absolute value is greater than or equal to 1. So those two concern specific types of series. The other tests are a little bit more general to the kinds of series you can apply them to. So we talked about the comparison tests as well. There was 2 of those. We had the direct comparison test, and then we had the limit comparison test. And remember, the purpose behind these tests is to take your series that you're testing for convergence, which may or may not be all that easy to work with, but compare it to a series that is easy to determine the convergence or divergence of, or just a series that you've already worked out the convergence or divergence of. So for these types of tests, typically you're comparing your series to something that's like a geometric series or a p-series. It doesn't have to be one of these, but oftentimes it is, because these 2 series are very easy to check for convergence. And you just want to see, is there a way that I can naturally compare the terms of my given series to a series of one of these forms to apply one of these comparison tests? So this one ends up being useful quite often. Number 5, we have the alternating series test. And remember, alternating series are series of the form, or of a form where the sign of your terms alternates between positive and negative repetitively for the whole series. So alternating series have a fairly straightforward test. There's just 2 things we're looking for. If you take the absolute value of all of the terms, so if you make them all positive, if after doing that, the sequence of terms that results, if it is a decreasing sequence, and if the limit of your sequence of terms goes to 0, then that implies that the alternating series would converge. You can even be a little bit more general than that. We've seen this before. It's okay if, for the first of those conditions, if after you take the absolute value of all of your terms, it's okay if the sequence isn't decreasing from the start. In fact, for the first finitely many terms, doesn't matter how many, the sequence can kind of do whatever it wants. It just needs to eventually be decreasing. So that gives us a little bit more power behind this test, because sometimes, as we've seen before, we don't get the decreasing trend in our terms right away, but that's still fine. Number 6 and number 7, we just talked about in the previous section, and number 6, the ratio test in particular, is one we're going to use a lot in the remaining sections of this chapter. The time that you want to use the ratio test to test for convergence for the types of series we've seen so far are typically series where the terms have factorials in them, or other kinds of products, even things raised to the nth power. Which oftentimes, if something's raised to the nth power, we tend to use the root test for those, but the ratio test can also be useful in those cases. The reason this is useful in those situations is because things that involve a lot of multiplication, like factorials or other kinds of products, will have a whole lot of cancellation once you set up the ratio in your ratio test. So the ratio test has the ability to simplify the thing that we're taking a limit of. Now, the ratio test, as useful as it is, it's not useful all the time. Like we said, there's other series tests up above here, which we may use in place of the ratio test. And the ratio test can also be inconclusive. Remember, if the limit of this absolute value of these ratios goes to 1, then the series doesn't give us information. We need to know if it's greater than 1 or less than 1. In addition to that, the ratio test has a little bit of extra power, because not only will it show if a convergent series is actually convergent, if that limit goes to something less than 1, but it will also imply something stronger, which is absolute convergence, which is a useful thing to know sometimes. Skipping down to the root test here. The root test is similar to the ratio test, except instead of taking the limit of the absolute value of the ratio of your consecutive terms, we're doing the nth root of the terms of the sequence, and then of the sequence of terms, and then we're taking the limit as n goes to infinity. But the root test is generally useful in slightly more restricted cases than the ratio test. We're specifically interested in using this test when we see that the terms of your sequence can all be represented as something to the power of n, because then the nth root will cancel that power out. Finally, way earlier in this chapter, we talked about the integral test. The integral test is a test that's useful for testing for convergence or divergence, but more often than not, if we're testing a series for convergence or divergence, we'll be able to make that distinction or that determination using one of these previous tests. The integral test really ends up being kind of the last resort, because it has a lot of conditions that the function that we're using has to satisfy. It has to be decreasing, continuous, and the limit has to be, it has to be, decreasing and continuous, and all the terms have to be positive as n goes from 1 to infinity. And then we define a real valued function that agrees with the terms of our sequence for all of these positive integers n. And then we have to compute an improper integral. So this can be a useful test, but sometimes computing that integral can be very difficult. So, this is, again, that's kind of your last resort. The integral test is not really what you want to start with. All right, so now that we've kind of covered the different strategies for testing series for convergence or divergence, let's go ahead and do a few examples where we can apply this. Okay, so to start, we have this series right here, n goes from 1 to infinity, n cubed plus 1 over n cubed plus 4. And the strategy that we looked at on the previous page said that the first thing you should do is check your test for divergence. So this, if I take the limit as n goes to infinity of n cubed plus 1 over n cubed plus 4, you should see that you have an indeterminate form. You end up with an infinity over infinity type of indeterminate form. But we have encountered enough of these types of limits to know what to do with them. So just as a reminder, we have a rational expression here where there's a polynomial in my numerator, a polynomial in my denominator, and the degrees of those polynomials agree with each other. They're both third-degree polynomials. When you get that kind of an expression, when you have polynomials of the same degree in your numerator and denominator, then the limit as n goes to infinity of this expression always goes to the leading coefficient of this polynomial over the leading coefficient of this one. It's not hard to show why that's the case, but we've been using that fact pretty regularly up until this point. So this limit is equal to 1, which is not 0, which means this has to diverge. So this diverges by the divergence test. Now, I know the book calls it the test for divergence. I call it the divergence test. Same thing. It's just different ways of saying the same thing. Okay? And you've probably noticed that I've been doing this in the examples up until this point as well. But one thing you want to make sure you're doing when you state that a series either converges or diverges, state the reason. So we have all of these tests. You want to cite those. I don't want to just say diverges. I want to say it diverges because of this thing, this divergence test that we've talked about. Let's take a look at another one. Here we have the series as n goes from 1 to infinity of 1 over n plus 1 over n factorial. Now, if I took the limit as n goes to infinity of this, both of these denominators are going to infinity. This one way, way faster than this one. And my numerators are both constant. So these are both going to go to 0. So the limit of the sequence of terms will go to 0. So what that means is I cannot use my divergence test to say that this diverges. Does that mean that this converges? No. In fact, this actually is a divergent series. It's just that our divergence test is not going to detect that. So let's try something else. When I look at this, I see that 1 over n there, and I immediately think of the harmonic series. The harmonic series we've seen is a divergent series. And so it seems like a good idea to compare this to our harmonic series. So how does 1 over n plus 1 over n factorial compare to just 1 over n? Well, I'm taking this 1 over n and I'm adding another positive number to it, which means this will always be greater than this. Now, because this series diverges, so the series as n goes from 1 to infinity diverges, because it's the harmonic series, so we already know that. So this series, n equals 1 to infinity of 1 over n plus 1 over n factorial, this will also diverge, and it's because of the direct comparison test. Diverges by the direct comparison test. Okay? And really all I needed to do was show that this inequality holds for all values of n. This will always be greater than this. And if this diverges and all of these terms are bigger, then of course this one has to diverge also. It's pretty good. Let's take a look at another one. I have this series, sine of 2n over 1 plus 2n. Okay, so when I look at this, I kind of think, yeah, I would like to maybe apply a comparison test to this as well, because I see this 2n down here. That makes me think of the series 1 over 2n, which is a geometric series. It's a geometric series that has 1/2 as its common ratio. And so that would be a convergent series. If I can somehow show that this sequence of terms here, term for term, are less than the terms of that series, that 1 over 2 to the n, then I can apply the convergence test. But there's one little problem with this. The convergence test has a condition on it which says that the terms of your series have to all be positive in order to apply that test. And the sine function does not always give us positive numbers. For certain values of n, this will actually come out negative. So what do we do about that? Well, what I'm going to do is, instead of testing this series directly for convergence, I'm going to test this series for convergence. So I'm going to take absolute values of all of my terms. Now, why am I doing that? Well, by taking absolute values, I'm ensuring that this thing comes out positive, or at the very least non-negative. In fact, it will always come out positive because there are no values of n, no positive integer values of n that are from 1 to infinity that I can plug into this that would make this come out to be 0. But that's beside the point. By making this an absolute value, I'm ensuring that these terms come out positive, which means I can apply my direct comparison test. But what is this really? Well, if I take the series that has the sum of these absolute values, then I'm looking at, if I can show that this converges, then that implies that the original series absolutely converges. Remember, that's the relationship. So this we would say converges absolutely. But if I can show that it converges absolutely, we had a theorem that said that that also just means that the series converges just under the normal definition of convergence. So let's see what we can do with this. This thing, the absolute value really only needs to apply to my numerator because my denominator is already going to be positive no matter what. Now, sine of 2n, because it's the sine function, the 2n is not really the important part. The fact that it's a sine function means that this thing can never be bigger than 1. So this I'm going to say is less than or equal to 1 over 1 plus 2 to the power of n. But that's not quite the series I wanted, the type of term I wanted to compare it to. I wanted to compare this to 1 over 2 to the power of n. Because this, when my terms look like this, I have a geometric series. How do these compare? Well, here we have a larger denominator than over here because I'm adding a 1 to it. And a larger denominator means a smaller fraction. So if you notice, the absolute value of these terms will always be less than 1 over 2 to the n. So now I can say something like this. The series from 1 to infinity of 1 over 2 to the n converges because it is geometric with r equals 1/2, which is less than 1. Okay. In fact, I could even say the absolute value of r is 1/2. It's technically not necessary to state that, but that's how we state it in the geometric series test for convergence. So this converges because of that, but because these terms are all less than this, so I can say n equals 1 to infinity of sine of 2n over 1 plus 2n converges absolutely by the direct comparison test, so it converges. Now that might seem like a weird sentence to say it converges absolutely, so it converges, but remember, by saying that it converges absolutely, we're really saying that the series with absolute values in it is converging, but then that implies that this series also converges. So that's kind of what that extra little couple of words there is saying. Okay, let's keep going. We have 2 more examples to look at. So here we are taking the sum of these terms here, n squared times e to the negative n cubed. And as usual, what we would want to do here is take a look at the divergence test first to see if it diverges. Now this is the same thing as n squared over e to the n cubed. And if I wrote it that way, the e to the n cubed in the denominator gets really, really, really big really, really, really quickly. way faster than n squared does. So what ends up happening is the denominator of that expression overpowers the numerator, and the limit of those terms will go to 0. That's a very informal argument for why the limit goes to 0. You can make it more formal by applying L'Hopital's rule to it a couple of times, and you'll see that the limit goes to 0. So the divergence test does not tell us that this thing diverges. And if you were to go through several of your other tests, like your, geometric series, piece series, alternating series, all these other things, pretty much all of those tests don't turn up anything terribly useful right off the bat. So we're actually going to use the one test that I said you tend to not use very much, which is the integral test. So this is set up very well for the integral test because when I define this function, f of x equals x squared e to the negative x cubed. Remember, this is what we do with the integral test. We replace those n's with x's because we're thinking of this as a function of x now. And then I want to integrate it as x goes from 1 to infinity. Now, it does have to satisfy some particular criteria. It needs to be positive, continuous, and decreasing on the interval from 1 to infinity. I'll let you verify that. It does do that. It does exactly what we need it to do. So the integral test is usable here. If I integrate from 1 to infinity, this expression right here, so x squared e to the negative x cubed dx, remember that technically this is a limit. The limit as t goes to infinity from 1 to t of x squared e to the negative x cubed dx. There is a very obvious u substitution that I can use here. U is equal to negative x cubed, which means du is negative 3x squared. And I don't have a negative 3x squared, but I do have an x squared. So if I change this to say negative 1/3 du, now I have the x squared. And I need to remember my dx in there also. So here's where I get to use a u substitution. Now that negative 1/3 can be brought out of the integral and even out of the limit. I'm going to say that's equal to negative 1/3. Limit as t goes to infinity. Now my limits of integration have to change too. So if I think about it, 1, when I plug that in for x, I would get negative 1 here. T becomes negative t cubed. I'm plugging t in for this x to get the corresponding u value. But then everything in here just becomes e to the u du. Okay, that's an easy integral to do. The exponential function is its own antiderivative, so we can say this is equal to negative 1/3 times the limit as t goes to infinity of e to the u from negative 1 to negative t cubed, which is this, negative 1/3 times the limit as t goes to infinity of e to the negative t cubed minus e to the negative 1. Now, here's where the limit is going to be applied. As t goes to infinity, negative t cubed is going to negative infinity, and e to something that's going towards negative infinity is getting very, very small very, very quickly. So in the limiting case, that will go to 0. That goes to 0, which leaves me with negative 1/3 times negative e to the negative 1 power. The negatives cancel, and I get 1/3e as a final answer. So what are we looking for in the integral test? We are just looking to see if this comes out to a positive number. Because if it does, or not a positive, sorry, a finite number. It will be positive, but the important part is finite. So I'm going to say less than infinity. Now, technically, this notation is not correct because infinity is not a number. We don't compare numbers to things that are not numbers. But this is basically just a shorthand of saying this is finite. So because it's finite, then our series converges by the integral test. Okay? All right. Let's get one more in. So here I have a series of the form n goes from 1 to infinity, and then I have n to the 2n over n plus 1 to the 3n. This one seems to me like the root test would be a very good one to use. The ratio test might also work pretty well, but I can see that because there's so many n's in here, and that's a lot of things that are going to be replaced by n plus 1s in that ratio test. So the simplification might be a little bit messy. But the root test seems like a really good choice here, and here's the reason why. That series can be written this way. I can write these terms as n squared over n plus 1 cubed to the power of n. Because then I could use exponent properties to bring the n in and write that as 2n there and 3n there, which is what we had. Okay, so now if I wanted to apply the root test, I'm taking the limit as n goes to infinity of the absolute value of n squared over n plus 1 cubed. That whole thing gets raised to the power of n. And then I'm taking an nth root of this because it's the root test, but we can write that this way. Now technically that n is inside these absolute value bars, but since n only takes on positive integer values, then the thing in here will only ever be positive anyway. So the absolute value is unnecessary. We can get rid of it. And that opens this n and this 1 over n up to multiply together and cancel out. So I end up with this limit as n goes to infinity of n squared over n plus 1 cubed. So now looking at this, what can I say about this limit? Well, once again, we have a rational expression where I have a polynomial in my numerator, a polynomial in my denominator, only this time the degrees don't agree. I have a second degree polynomial up here, and if I were to expand n plus 1 cubed out, I would see that I get a cubic polynomial. So because my polynomial in my denominator has a higher degree than the one in my numerator, this will actually go to 0. And because we're talking about the root test, the important observation to make is that the limit was less than 1, which means that this is a convergent series. In fact, it's absolutely convergent. So I might just state that because that's more informative. Series is absolutely convergent by the root test. Okay, so hopefully those 5 examples give us a good kind of array or a range of different things or different tests rather that we needed to apply to solve them. The homework for this section will have you doing a lot more, but that you kind of want to follow that general strategy of how to decide which convergence or divergence test to use in different situations. That's it for 11.7.